Hello and welcome everyone to our physics class. Today we are going to start this chapter number 10, that is wave optics. The connection between light as a wave and as a ray of light. The connection between wave and ray of light that you are going to study in this chapter. The chapter is wave optics. Newton's corpuscular theory of light survived for quite a long time. He gave his corpuscular theory in the year 1665, in which light was considered as corpuscles. Corpuscles means particles, and they travel in a straight path. Then we took it as ray of light like this. It explains reflection of light, refraction of light, scattering of light, then dispersion of light. Those phenomena were explained by corpuscular theory of light. But when it comes to interference of light, diffraction of light, polarization of light, this theory fails to explain. The biggest blow of this theory came in the year 1801. 1801, when Thomas Young presented his double slit experiment that explains interference of light. Light in the form of wave. Light in the form of wave. This theory was unable to explain by corpuscular theory. So you can see the difference in the year, and nearly 145 years after that only people came to know about the wave nature of light. But there was one Dutch physicist called Christian Huygens. He gave his theory in the year 1678, and his theory was based on Huygens principle. We call it as Huygens principle, and in this theory he considered light as wave character. But due to the popularity of Newton, more faith on Newton, people were still believing this corpuscular theory of light. But when this interference pattern was explained in the form of wave by Thomas Young, then it was like an eye-opener that light does not travel in the form of particles, it travels in the form of wave. Then they came back here to Huygens principle, and then this principle was modified by Fresnel, and then the wave theory of light started its journey. The real climax came when this wave theory of light could not explain Hallwatch and Leonard's experiment. Or Hallwatch and Leonard's observation. In the year 1900, they too observed that when light of certain intensity falls on a metal surface, electrons are ejected. And the kinetic energy of the electron does not depend upon the intensity of light that it falls on the surface. So this observation was seen by Hertz as well in the year 1880. He saw it much earlier than Hallwatch and Leonard. The observation made by Hertz, Hallwatch and Leonard, that the photoelectric effect was later on explained by a physics giant. His name popularly you know, Albert Einstein, in the year 1905. So it is based on particle theory of light. Later on, this one photoelectric effect was studied in chapter 11 under the heading dual nature of matter and radiation. That means radiation possesses both wave as well as particle character. That was the conclusion made. In this chapter, wave optics, we are going to learn four things under this. The first one, that is your Huygens principle. The next thing that you are going to learn is about interference. Of light waves, how they interfere with each other. The third thing you are going to study is about diffraction, the bending of light rays as it strikes the sharp edges. And the fourth thing that you are going to learn here is polarization. Polarization of light. These four phenomena you will study under this chapter, which we call it as wave optics. But now, due to lockdown, this portion of the chapter is eliminated for the year 2020-21 batch. So we'll be dealing with Huygens principle, interference of light, and diffraction. Now, to start with Huygens principle, you need to know some terms first of all related to the principle. These are all based on wave theory of light. The first thing you have to know is about wavefront. Wavefront. Wavefront, when we say, it is the locus of all the points in the same phase of vibrations. There are three types of wavefronts. Suppose this is a source of light. We know that the light rays, it will go radially like this, somewhat like your electric field lines when you study about static electricity. Now, if you take the locus of all the points in the same phase of vibration, that means time factor will come. After 1 second, suppose it reaches here, this light ray reaches here, this light ray reaches here. I am taking the time interval 1 second. Then if you join all of them, then you get the locus of all the points, the combination of all the points in the same phase of vibration. They will be in the same phase of vibration because they are from the same source. This we call it as a wavefront. This is your wavefront. But what is its nature? Then you will say spherical wavefront. Like this, under 1 second, suppose the particle will reach here, here the light ray will reach here, here. Then if you join them again, you will get another spherical wavefront. This is another spherical wavefront. So wavefronts are of three types. The first one is your spherical wavefront that you can see on the board. The second one, let us see, cylindrical wavefront, number 2. Cylindrical wavefront, you will get it from a linear source. Suppose this is your linear source of light. Then the light rays, they will travel in all the directions like this. It will grow this way. It will grow. So from the same point, if you take like this, it will appear like circular. At every point it will get circle, then overall it will form a cylindrical wavefront. These arrowhead lines that you can see, these are light rays. So it will form a cylindrical wavefront. This is your cylindrical wavefront. Then the third type of wavefront, that is your plane wavefront, which you are going to use very often. The third one, plane wavefront. If this spherical wavefront, it goes like this, it grows and goes. From far, if you look, a part of it, if you take it, then it will look like a flat surface. Even this one, if it is growing this way, from far, if you look that surface, a part of it, if you take it, then it will look like a plane wavefront. We call it as plane wavefront, and it will grow like this. Light rays, they are coming this way. Somewhat it will look like this. This is your plane wavefront. So these are three types of wavefront. This one is nothing but produced from spherical, either spherical or cylindrical wavefront. We are taking it from far and we are taking only a part of it. Then it will look flat like this. That we call it as plane wavefront. One thing you have to know it here very clearly, that this light ray and this wavefront, they are always perpendicular to each other. Here at all the points they are perpendicular. Light ray and the wavefront, they are always perpendicular to each other. Light ray and the wavefront, they are always perpendicular to each other. This dotted line that you can see here is your wavefront. Here I have drawn solid only, like a cylinder. But you should know that light ray and the wavefront, they are always perpendicular to each other. Now to discuss about Huygens principle, let us see what is Huygens principle. Huygens principle, it is essentially a geometrical construction. This is just a construction. Suppose if we know the wavefront at an earlier instant of time, then at a later instant of time, what will be its shape? What will be the shape of the new wavefront? That you can come to know through this Huygens principle. It states like this. The first statement, it is given in two steps. It is given in two steps. Every point in the primary wavefront is a source of secondary disturbance. And the secondary disturbance gives rise to wavelets. Which travels equally in all the directions. This is the first statement given by Huygens. It says like this. I'll draw here. Suppose this is a source of light. And you know that the light rays will spread equally in all the directions. At a particular distance from the source, if I draw, suppose this is the wavefront I know from before, as I have discussed about spherical wavefront. You can remember, I think, a source of light, then it will emit light in all direction like this. Light rays, if you draw, it will look like this. At a particular instant of time, if I take this point, then I can draw one wavefront, a spherical wavefront. So if this is your source, suppose this wavefront you know earlier, at earlier instant of time you know already. Let us take the time as t equal to 0. After time t, suppose from 0 to t, how much or how the new wavefront will appear to be. Then you will follow this. Every point in the primary wavefront, this is your primary wavefront. Every point in the primary wavefront is a source of secondary disturbance. Now, what is the secondary disturbance? Every point. So here you can take any point, as much point as you like, you can take it. I am taking few here, you can see. I have taken 1, 2, 3, 4, 5, 6 points only I have taken. It is a source of secondary disturbance. Then you have to think that in a pond, if you drop a stone, then how the ripples are formed. Like that you have to imagine. Suppose at this point, it started growing. Slowly it will grow. After say some few seconds, it has grown up to this much. It has become this much bigger. Then during that same time, this point also is growing. So it will form, the secondary wavelets will grow by this much. Again at this point, it will grow by this much. This point also, this is happening at the same time. So you have to imagine all the points on the primary wavefront as a source of secondary disturbance. This secondary disturbance gives rise to wavelets. These ripples that are formed by the secondary disturbances, that is the particles, gives rise to secondary wavelets. These are your secondary wavelets, and they travel equally in all the directions. They travel equally. This is three-dimensional. They travel equally in all the directions. That is the first point, what Huygens has given us. Then the second point, the tangent envelope. To these secondary wavelets gives us the new wavefront. At a later instant of time. Or at a later instant. Now we are going to draw a tangent to these secondary wavelets. Now to draw a tangent, all of you know what is a tangent. I think a tangent is a straight line that touches the circle at only one point. So this line is your tangent to this circle with center O. Now you have got a lot of circular structures here, dotted lines. Now if I draw a tangent, I can draw here like this, touching all the secondary wavelets. So this will be at t equal to, suppose, say t. This was the starting time that you knew the wavefront from before. Then after time has changed to t, say 5 seconds or 2 seconds or 3 seconds, what is the shape of the new wavefront? Then this will get it the new wavefront. You get the new wavefront. So this is your Huygens principle. This is only to construct a new wavefront at a later instant of time when you knew a wavefront at an earlier instant of time. Now you may be thinking that why I am not drawing this side. backside. Why I am not drawing the tangent backside near the source of light? Here, this one mathematically, Kirchhoff has given us a relation, and it has been proved mathematically that this side the amplitude will be less, towards the source the amplitude will be less or nearly equal to 0, and only the forward direction you will get the new wavefront. This part you will study later on in higher classes, in the relation that was given by Kirchhoff. Now let us see how we can prove the laws of reflection based on Huygens principle, that is your wave theory. According to wave theory, suppose this is the reflecting surface that I am taking, X and Y. This is your plane mirror. The top surface is the reflecting surface, this side. Downside is painted. Suppose if I draw two rays of light this way, parallelly they are coming and striking the mirror. Let me number this as 1 and 2. These are the two light rays. When this first light ray reach the glass surface, strike the glass surface, that time this ray will not reach the glass surface. Suppose it is here, let me mark it as B, and this one let me mark it as A. If I join this A and B, I'll get the incident wavefront. And the secondary wavelets that will grow from point A and B, let us assume like this, from point B, suppose growing, it has reached here. It has struck the surface XY. Let me draw this way. So one small curve you can give. The time it takes to reach from B to C, during that time this wavelet also will be growing. It will reach somewhere here like this. If I draw a ray of light this way, then this wavelet also will grow like this, like this, like this, like this, like this, it will grow like this, it will reach. So it will take some time to reach from A to D. The time taken to reach from B to C and the time taken to reach from A to D both will be same. Let us assume it as T. It took time T to reach. T is equal to T, and this is the initial time. Let us take T equal to 0 here. This tangent if you draw now, then you will get a reflected wavefront. The curve you can draw this way. You will get a reflected wavefront. So DC will be your reflected wavefront. Now this ray, if I extend it, again they will reflect back parallelly. They have come parallel way, so they will get reflected parallelly. Now let me write down AB is the incident wavefront, CD is the reflected wavefront, now time taken to reach from B to C, time taken for the wavelet to reach from B to C, and time taken by the wavelet to reach from A to D, and time taken by the wavelet to reach from A to D are equal. Let it be T. Now, if the time taken is equal, then we know that the speed of light in one medium will remain the same. Let the speed of light in air, suppose you are doing it in air, this one, you are keeping the mirror in air. Let the speed of light in air equal to V, suppose. Then what will happen is this distance from A to D and the distance from C to B, they will be equal, because distance equal to speed into time. Distance AD will be equal to distance BC, both will be equal to V into T, speed into time. So I'll write down here, distance AD will be equal to distance BC, what will be equal to V into T. Now let us discuss about their angle of incidence. When a ray of light comes and strikes here with a normal, you get the angle of incidence between the incident ray and the normal. Let me mark it as MA is your normal. Now, we know that the light ray and the wavefront, they are perpendicular to each other. So this remaining angle will be 90 minus I. This angle will be 90 minus I. Now again, this normal and this reflecting surface is 90 degree. So this incident wavefront with the surface will be angle I. This is 90 minus 90 minus I. 90 degree minus 90 degree minus I. So it is 90 degree minus 90 degree, minus into minus will become plus I. It will get cancelled, it will get angle I. So ultimately what you have to remember is the incident ray and the normal makes an angle called angle of incidence. And when we talk in terms of wavefront, the incident wavefront with the surface will make the angle of incidence, that is I. This is the surface and this is the wavefront. Likewise here also, if you draw a normal here, suppose NC is your normal, then according to wave theory we know that this is angle R. But now with the wavefront and the surface will make an angle of reflection that is R. This is your wavefront DC and XY is the surface that will give us the angle of reflection R. Same as how I have shown you here. This way also you can do. This is 90 degree ray of light and the wavefront, it is 90 degree here. So this angle will be 90 minus R. And again normal and the surface is 90 degree. So 90 degree minus this 90 minus R will give you R. Like this you can find out angle I and angle R. You can mention it also. Here angle BAC is equal to I and angle DCA is equal to R. Now if you take these two triangles now, BAC, this is a right angle triangle. Here the angle is 90 degree. Wavefront and the ray. Here also wavefront and the ray will make an angle of 90 degree. So if you take these two triangles ABC, triangle ABC will be congruent to triangle ADC by RHS congruency. Or RHS congruency criteria, because this is the common surface, there is the hypotenuse. This distance BC is equal to distance AD and these two angles 90 degree each. So it will form RHS congruency. So if the two triangles are congruent, then their corresponding parts also must be equal. BC, the corresponding side is AD. So opposite of BC is angle I and opposite of AD is angle R. So from there we write angle I is equal to angle R, corresponding parts of congruent triangles. This proves first law of reflection. Now to prove the second law of reflection, wavefront, our incident wavefront is AB the reflecting surface that is XY and the reflected ray is a reflected wavefront DC are all perpendicular to the plane of the board. Now for you it will be paper. Are all perpendicular to the plane of the board. This is the mirror, this is the incident wavefront, this is the reflected wavefront. They are all perpendicular to the paper. Are all perpendicular to the plane of the paper. Therefore, the incident ray that is ray number 1, this one I am taking, incident ray, the normal is for MA and the reflected ray I am taking this one AD, which are respectively perpendicular to incident wavefront, the reflecting surface and the reflected wavefront all lie on the same plane, that is the plane of the board. Now here it is like this: the incident wavefront, reflected wavefront, and the reflecting surface all are perpendicular to the board. And in turn again, the incident ray, normal, and the reflected ray are perpendicular to the incident wavefront, the reflected wavefront, and the reflecting surface. So one is perpendicular on the other. So if this incident ray, normal, and reflected rays, you already know that they lie on the same plane, then this tree also, the incident wavefront, the reflecting surface, and the reflected wavefront, all will lie on the same plane. They are mutually perpendicular with each other. Now let us prove the laws of refraction based on Huygens principle, that is on wave theory. Let us take XY as the refracting surface. This is air, suppose. The speed of light in air, let us take it as V, or let us take it as C. Speed of light in air, and this is your rarer medium, and this is your water, say, denser medium, and the speed of light, let us take it as V in water. Like earlier case, we will draw two light rays this way. We will number it as 1 and 2. Suppose this is the second light ray. They are coming parallel like this. Then when this ray has struck the interface XY between air and water, then that moment this second ray will be somewhere here. That will give us the incident wavefront. We write it as AB. Then by the time the wavelet starts to grow from B and A, by the time it reaches from B to C, the same time it will take by the wavelet to go from, suppose this is the wavelet, one structure like this, it's going and coming. Then during that time it has struck the interface, so it will bend towards the normal a little bit and come like this, the reflected ray. And then this wavelet also will grow and reach, suppose somewhere here it has grown, it has reached like this. The time that this wavelet has grown up to this point C, how long it took? During that time, the wavelet from A also will grow and reach at some point. Let us take it as D. Now this tangent envelope, if you draw here according to Huygens principle, you get the refracted wavefront. This light ray also, it will pass like this, little bit will come down towards the normal. If you draw the normal like this, that will be Mn. Let it be PQ. This is P, this is Q. So these are the normals. Now this is the angle of incidence, and as we know from the earlier case that the incident wavefront and the surface gives us the angle of incidence, and the reflected wavefront with the surface will give us the angle of reflection R. The ray and the wavefront, they are perpendicular to each other. This also you know. Here also the ray and the reflected wavefront will make an angle of 90 degrees here. These things you know from before. So let us write down. AB is the incident wavefront. AB is the incident wavefront, and DC is the reflected wavefront, and DC is the refracted wavefront. PQ and Mn are the normals at point A and point C. PQ and Mn are the normals to the surface at points A and C. Let C be the velocity of light in air. C be the velocity or speed of light in air, and V be the velocity or speed of light in water. Then we'll write about this. The time taken by the wavelet to reach from B to C is the same as the time taken by the wavelet to reach from A to D. Time taken by the wavelet to reach from B to C is the same as the time taken by the wavelet to reach from A to D. Let the equal time taken be T. Let us take it as T. Say T. Now we will find out the distance BC and we will find out the distance AD. Distance BC is equal to, distance is equal to velocity into time. Velocity of light in air is c, so it will be c into t, and distance is equal to a distance AD. It is equal to, here speed is v, so time is t. Like this you can find out the distance. In the earlier case, distance were same. Both the speed of light was in the same medium, so it was vt. But now mark it. It is different. It is in air, it is different. In water, it is different. In air, we are taking C, and in water, we are taking this V. Now here, what we'll have to do is in triangle ABC, by using trigonometry, you'll find out sin I, and triangle ADC, by using trigonometry, you'll find out sin R, and we'll divide them. And then we'll see what will be the value of refractive index. If you get the relative refractive index of medium 2 with respect to medium 1, then our Snell's law is proved. That is, the first law of refraction is proved. You can remember, I think, I'll write down here sin I by sin R is equal to refractive index of second medium with respect to first. And in our case here, water, we are taking it as V. It is mu2 by mu1. So velocity of light and refractive index are inversely proportional, so you should get C by V. You should get C by V. Medium 2, it is V, so it will come down inversely proportional. Medium 1, it is C. This is your medium 1 rare medium. This is medium 2 denser medium. It is C. Medium 1, it is C, so it will come up. They are inversely proportional to each other. So we are going to prove the sin I by sin R equals C by V. It will give us our Snell's law of refraction. Now let us see in triangle, in right triangle ABC, in right triangle ABC, sin I, let us find out what will come out. Sin is defined as perpendicular, opposite of the angle, perpendicular to its hypotenuse, opposite of 90 degree. This is BC by AC. This is BC by AC. And BC, you know, it is C into T. C into T divided by AC. Let us mark it as equation number 1. Likewise, in this right angle triangle also, you will find out sin R in triangle, right triangle ADC. Sin R is equal to, opposite side is AD by hypotenuse, that is AC. AD by AC. AD by AC. AD, as you know, it is distance. AD PT divided by AC. Let us mark it as equation number 2. On dividing equation 1 and 2, sin I by sin R is equal to sin I, you can see it is CT by AC. CT by AC. Multiply by, if you do, it will be upside down, AC by VT. AC by VT. These two you can cancel it out. Time also you can cancel it out. So you will get C by V. You can see here, C by V you are getting it. That means it is equal to relative refractive index of medium 2 with respect to medium 1. This proves Snell's law of refraction. This proves Snell's law of refraction, or your first law of refraction also you can say. The number 1 and number 2, first law, second law, whichever you want to make first, it's up to you. Whichever you want to make second, it's up to you. And then the second law, if you say that the incident ray, the normal, and the refracted ray all lie on the same plane, then you can write like this: the incident wavefront that you are taking it as AB here, the interface separating the two media, interface separating the two media, and that is XY, and the refracted wavefront is CD, are perpendicular to the board. No, for you it will be paper, perpendicular to the paper. Therefore, the incident ray, let us take it as ray number 1. The first normal you can take PQ, and the refracted ray, the first refracted ray, that is AD, are respectively all perpendicular to, are respectively all perpendicular to incident ray, perpendicular to incident wavefront AB. The normal PQ is perpendicular to the refracting surface XY, and the refracted ray AD, refracted ray is AD, perpendicular to refracted wavefront CD. All lie on the same plane. Like this you can write down theoretically the second law of refraction.
Let us see the behavior of prism, lenses and spherical mirrors towards plane wavefront.
When you keep a plane wavefront in front of a prism, suppose this is your prism ABC. If you keep a plane wavefront in front of it, this is your plane wavefront. Then, as we know that this portion of the mirror is thick, light will take time to come out of the prism, so it will move lately, whereas the upper portion, as it is thin, it will move faster, light will travel faster. So ultimately what you will get is a plane wavefront only you will get in a prism, but it will be inclined. This is your light ray, perpendicular to the wavefront. You will get a plane wavefront. Like these diagrams, it is to come in exam. From exam point of view, these are important, you need to know. Now let us see in a convex lens. We take the second focus here. In a convex lens, if a plane wavefront comes, it's not necessary that you have to draw this principal axis, but as I have just drawn, let it be. Suppose this is your plane wavefront. It's coming like this towards the lens. We know that in a lens, this portion of the light ray comes out slowly because this is thick, and this, as it is thin, it will come out faster. This is fat, so it will come out lately, and again here this ray, if it comes and strikes here, it will come out faster. So it will look like a spherical wavefront. This is a new wavefront. This is a plain wavefront. And if you can draw this way, it is better. This way you can draw the light rays. Plain wavefront. And this will be your cylindrical, spherical wavefront. So it will look like this. So you have to think it very carefully. Fat region will come out slowly. The thinner region will come out faster. So it will become spherical. Now let us say about a concave mirror. Suppose this is your concave mirror. If you keep a plain wavefront in front of it, this is your wavefront, the plain wavefront. This is plain wavefront. The light ray, you can see very clearly here. It will take time to reflect back because the distance from the plain wavefront up to here it is less, and here it is more. So this will go, strike and come out faster. So here also it will go and come out faster. But this, as this distance is more, it will come out slowly. So here also it will look like a spherical wavefront, like this will appear. Light rays will come out like this way. So this also will be a spherical wavefront. Like this, you can do for convex mirror, you can do for concave lens, and different optical instruments. You can allow the plain wavefront to go and strike and think it properly, and what will be its shape, that you have to know how to draw. Thank you and have a nice day. In today's video, we'll end up here. Next class, we'll start with interference superposition principle of waves.